So first, we will describe graphs used in kinematics. So we will see how to relate velocity, position, acceleration, and time through graphs. In order to if you want, graphical conclusions, we should understand the relations between acceleration, velocity, position, and time. So first, for example, if I consider the following graph, if they give me as function of time, okay? And from this graph, I want to make conclusion about the velocity. I should go back to the relation between velocity, position, and time. From this relation, V is the derivative of position with respect to time. And this graphically means what? What can you deduce if I tell you that the velocity is the derivative of s with respect to time? Graphically, this means, yes, graphically, this means that I can, at any time t, okay, draw the tangent line to the graph, and the slope of this line will represent the velocity. Because mathematically, if I have a function and I draw the tangent at a certain point, I can say that the slope of this line is equal to the derivative of the function. So if they give me graph as function of time, I can deduce the value of the velocity at any point. And then taking several points, I can construct the velocity diagram. So I can deduce the velocity diagram from the position versus time diagram. Now, I can do the same between velocity and acceleration, because also acceleration is a derivative of velocity with respect to time. So if I have v function of t, I can deduce a function of t by taking several points and of the graph, and at each point I can draw the tangent line. And when I draw the tangent line, I graphically determine its slope. So I take any 2 points of this line and I measure with a rule what is delta v here. So this is, let me choose another color. So this is delta v. This is delta t. So if I do the ratio of delta v over delta t, I get the slope of this line, which will represent the acceleration at point t1. And I can do the same procedure for several points and then draw the graph of acceleration. Now, we can do this analysis in the reversed way. So sometimes they can give me a function of time and I want to deduce v function of time. How to do this? If I have a function of time, I go back to the relation between a, v, and t. So we know that a equals to dv by dt. And since the graph of a is provided function of time, so I can take dt to the other side and then say that a dt is equal to dv. And now I can find the variation of velocity between any 2 times. So if I take, let's say this is t0, and this is another time here, t1, for example. And I want to determine how the velocity is varying between t0 and t1. So if I integrate this relation here between v0 and v, and this relation here between t0 and t, and I try to do a graphical interpretation about this. So if I'm integrating between t0 and t1, this will correspond to v1 minus v0. And graphically, how can I determine integral a dt between t0 and t1? What should I do? You remember mathematically the integral represents what? Exactly. It's the area under the curve. So if I'm able to measure this area here, I can determine the value of delta V. And then I just need a boundary condition to find V1. If I want to calculate V1, they should give me at least one value of velocity at any point. So for example, if they give me at t equals 0, what is V0? I can deduce then the velocity at any other point. So just in the integral procedure, in the reversed way, I need one boundary condition to draw my graph. If they don't give me a boundary condition, I can just draw delta V, function of time, but not V. Okay, so this is how I can determine the graph of velocity given the graph of a function of time. Now, I can do the same for if they give me the velocity graph and I want to find the position graph, because the relation is similar. Since V is ds by dt, if I do separation of variables, I can say that delta S is integral V dt. So if they give me V function of time, I just need one boundary condition. For example, if they tell me that at t equals 0, I have S equal to S0, then at any other point of interest, to find what is the value, let's say this is 0.1, to find what is S of 1, all I have to do is to say that delta S, which is equal to S1 minus S0, is equal to integral between 0, if I give you S0 at t equals 0, so between 0 and t, 1, and then I go to my graph here. This is t1. I determine this area, and this area will be equal to S1 minus S0. And since I know S0, I can find the value of S1. And I can do this for several points and draw my graph. Any question on this? Okay. We have also several other relations that are independent of position. So we know we have already established together that if we have a, let's say, given function of position S, then we can use other differential equation to deduce velocity. We know that VdV is integral AdS. So if I start from this relation, and given that A is given function of S, and I want to deduce V, already I can say that since I have a function of S, so integral AdS between any 2 points S0 and S1 can be determined graphically by the area under the graph between the 2 points S0 and S1. So let's say this is S0 and this is S1. This will be the area limited by these two, the area here in red. And then to find the corresponding value of V, I integrate the second side between V0 and V1. And the integral of V function with respect to V is V squared over 2. So I get V1 square minus V0 square over 2. Now, also here I need a boundary condition. If they give me for S equal S0, what is V0? I can deduce then the value of V1 square. So I can plot V1 square function of S. And if I know the sign of velocity, if it's positive or negative, I can draw V function of S. Okay. Now, we can do it in another way sometimes. If they give me V function of S, and I want to deduce a function of S, what should I do? I go back to the definition. If I have V function of S, I want to relate A to V and S. So I go again to the differential equation AdS equal VdV. And I say that I need to take ds to the other side because the graph provided for me is v function of s. So then I can write that the acceleration is v dv over ds. Now, if I do an interpretation of this formula means that at any position s, okay, if I want to find the corresponding acceleration, first I should determine what is the velocity at this point. I can do this graphically because I have v function of s. So all I have to do is to read the corresponding value of velocity for this position s. So let's say I am interested at a1 at s1. So for s1, I read the corresponding velocity v1. So I say that a1 is equal to v at point 1 times the derivative of velocity with respect to s at point 1. And graphically, this represents the slope. So all I have to do then is to draw the tangent line at this level. Okay. And then I take any 2 points. It's a straight line. I can take any 2 points of it and determine the slope delta v over delta s. This will give me dv by ds at this point 1. And I multiply the velocity at point 1 by the slope at point 1 to get the corresponding value of acceleration. So this is how we can use graphs to determine relations between velocity, position, acceleration, and time. Any question on this? Please stop me. Yeah.
I didn't really understand the first one.
Okay.
The one you explained just before this one.
Yes. Okay. So if I give you the graph of acceleration, function of position, and you want to deduce the graph of velocity, okay, you should say, I should relate velocity to a and s. So this is why you will first think about the relation independent of time between av and s, which is ads is equal to vdv. Okay. Now, since you have already in your graph a given as a function of position, okay, then from this graph you can deduce the integral of ads between any 2 points. So for example, if I consider, let's say this is point s1, okay, and this is point s2. If I tell you what is integral ads between s1 and s2, all you have to do is to go to your graph and plot these lines. They will determine an area, okay, under the curve. This area represents integral ads between s1 and s2. Now, this was equal to what? So this area, which you can determine from your graph, is equal to integral of vdv between 2 points v1, points 1 and 2 corresponding to v1 and v2. So if you integrate this side, you have to integrate function v with respect to variable v. So the integral is v squared over 2. So you will get v2 squared over 2 minus v1 squared over 2. So let's say I gave you one boundary condition. I gave you the velocity at point 1. I told you that at s1, v1 is given. Deduce velocities at other points. The area is determined graphically. v1 is provided as boundary condition. From this equation, you can deduce the value of v2 squared. And then, knowing the sense of motion, if it's up or down, or if it's in the positive or negative direction, you can determine v2. So let's say v is positive. So you do radical and you find the corresponding value of v2, and you can draw then the velocity at any point you want. This way you can obtain the graph of v function of s.
Okay, thank you.
Welcome. Any other question?
Professor.
Yes.
Professor.
Yeah, I'm hearing you.
Can you hear me? I wanted to ask you just to make sure.
Yeah.
So the integral of ADS graphically
Yeah.
is the area, and
Yes.
dv over ds graphically is the slope. Am I right?
Yes, exactly. It's the slope of
Okay,
V with
so
respect to S.
okay, so what does v times dv, what does it mean?
This means that from the relation, from the differential equation, to get the acceleration, you should at a certain point multiply the velocity by the slope. Okay. So when you
Yes, I'm
have
finished.
V function of time, the acceleration just represents the slope of velocity with respect to time. However, if I give you V function of S, the acceleration is not equal to the slope because A is equal to the slope of when you take V function of time. But when you take V function of S, we derive together that the acceleration will be equal to the value of the velocity at this point times the slope of V with respect to S. Okay. So keep in mind here it's with respect to time. Here it's with respect to position.
Yes, I understand. يعني v dv لحالة doesn't mean anything.
V dv لحالة yes يعني ما انت بدك تجيب A. So you should take the S to the other side. Yes, V dv
Yeah, I
لحالة
know.
لها معنى. V لحالة
I'm...
هي velocity graphically. dv by ds هي slope graphically.
Okay. Okay, Professor, thank you.
Welcome. Let me check your chats. Eli, it's fine for VDV equal ADS. Eli, you asked a question in the chat. It is fine, or you want me to repeat anything? I already repeated for your friend. Okay, if you want anything, let me know. Okay, so let us continue. We'll do together a series of problems to see how we can use sometimes graphs to do some interpretations, okay? We have a bicycle moving along a straight road such that its position is described by the following graph. We want to construct the VT and AT graphs for t between 0 and 30 seconds. Look, if they don't specify for you the method to use, you can use or analytical way or geometrical way. Okay, so here, because they provided you with equations of position, then it's easier to work with the analytical way because the graphical method will take time. So if I want to get V, I should take several points, and at each point I should find the slope to determine velocity. And for the straight line part, it's very simple. When you have S rectilinear with respect to time, what will be the value of velocity? Constant, and it's just equal to the slope. So you can just take any 2 points. So when you have linear behavior, it's very simple to determine the velocity value. You just take 2 points of your graph, and you say that the velocity is equal to the slope. So I have just to take delta S here over delta T. And I can read from these 2 points that delta S is 150 minus 30 equals 220 meters. And delta T is 30 minus 10 is equal to 20 seconds. So the velocity is in this phase is constant because it's a linear variation of S with respect to time. And it's equal to 120 over 20 equals to 6. Okay. Anyways, I also provided me with the function S function of time. So I can just say by another method that the velocity.
We derive it.
Yes, we derive it. So the analytical way is simpler sometimes. Okay, it depends on the problem. So if they give you the analytical equations, it's easier to derive. So the derivative is 6, and I found the same result, of course. Now, for this part here, Okay, it's not simple to do the graphical method. I should take several points. So here, for example, I can draw the tangent line at t equals 0. It's clear that my tangent line is horizontal. It has a 0 slope. So I can say that the velocity at t equals 0 is 0. And if I want to draw a graphic, sorry, if I want to draw graphically the velocity, I can take several points. And then from the slope, I can determine the value of v. And what is clear here is that the velocity is increasing because the slope is increasing as the time is increasing. Okay. Now, what is easier to do here is the analytical method. So I have S in this region given. S is equal to 0.3 t squared. So all I have to do then is to derive this relation with respect to time. So V is ds by dt is equal to 2 times 0.3t, so which is 0.6t. So as expected, V is linear with respect to time, because if S is second degree with respect to time, then velocity will be linear with respect to time, and acceleration will be what?
Constant.
Constant. So if I, for the first phase, I can directly say that A is the derivative of V with respect to time. So it's just equal to a constant equal to 0.6.
0.6.
Exactly. While for the linear part, S is linear with respect to time. So V is constant and A is 0. So when V is constant, the derivative will be of a constant is 0. So no acceleration. Okay. So here's the analytical method is simpler to use than the graphical one. As I told you, if they don't specify for you what to use, do what you want. Okay. We'll see sometimes that the graphical methods can be faster. So it depends. Here, the analytical method was faster. Let us do another problem and compare the analytical and graphical method. Okay. In the following problem, we have a test car starts from rest and travels along a straight track such that it accelerates at a constant rate for 10 seconds and then decelerates at a constant rate for the remaining time. Draw the velocity versus time and position versus time graphs and determine the time t prime needed to stop the car. How far has the car traveled? So I'll do with you both methods here, analytical and graphical, and we'll compare them. Okay. So first, what we know is the graph of a function of time, but in this graph, we have one unknown, which is t prime. So to find t prime, they gave us a condition. They told us that t prime corresponds to the time when this car will stop. So this means what? If the car will stop, what can I deduce?
V
that
equals
at
0.
Exactly. So the condition at t prime is velocity at t prime is equal to 0. Okay. Now I will use this condition to find t prime. Okay. Now, since I have a function of time and I want to find what is the time needed to stop the car, I should draw the graph of velocity and say that at t prime v is 0. So if I draw the graph of v, okay, so this is the axis of velocity, this is the axis of time, and now let us start. We have two phases, okay? In the first phase, between 0 and 10, my acceleration is constant positive. So my velocity, what can I deduce about my velocity then?
Increasing.
Increasing.
Very good. First, it's increasing because A positive. Second, because A is constant, how will be V?
Linear.
Linear with time. Okay. And the slope of V is equal to what? Is equal to the value of acceleration. So the slope of this linear variation is equal to 10. Okay. Now, since it's I am sure that here V is linear increasing. Okay. So I just need 2 points to draw the graph of velocity. First, they told me that the car started from rest. So I know a boundary condition. So it's linear and increasing, okay? And the boundary condition that I know
V0 equals
is
0.
that exactly at t equals 0, the velocity equals 0. So the first point I can put on my graph is this one, which correspond to t equals 0, v equals 0. The second point is at the end of my phase 1. We know that graphically, okay, the variation of velocity is equal to the area under the acceleration graph. I can easily calculate area 1. Area 1 is equal to 10 times 10 to 100, okay? And by definition, since A is dv by dt, so delta V is integral A dt. So what can I write then? I can write that the velocity at 10 seconds minus the velocity at 0 seconds, okay, delta V between these two times is equal to the integral of A with respect to time between 0 and 10, which is what graphically, which is the area. So I can write here that this is equal to A1. And since V0 is 0, so the velocity at 10 seconds is equal to the area limited by the acceleration graph between 0 and 10 seconds. And this area is 100. So I can deduce that the velocity value at 10 seconds is equal to 100 meters per second. Okay, so I can now place my second point. So this is t equal 10 seconds. This corresponds to a velocity of 100. So I can just put the point here. So let's say this is 100 meters per second. Okay, and now since I have 2 points, all I have to do, and I know the variation is linear, I just have to match these 2 points. And I get the variation of velocity in phase 1. Okay, now suddenly the car will decelerate. So I will move from positive acceleration to negative acceleration. But since this negative acceleration is constant, I can then say that here in this phase, V is still linear, but what?
Negative.
But no, not
Negative slope.
Negative slope.
Decreasing. Okay, yes, the slope is negative, so the velocity is decreasing. Okay, but it will remain positive because at the final time, what will be the value of velocity?
0.
0. So since I know the condition that at t prime the velocity is 0, I can just say that at t prime I will reach this level, and my purpose is to get t prime. Okay, I want to find the value of t prime. So what I will do then, I will join these 2 points and say, to get t prime, I know that the variation of velocity between these 2 points is equal to what?
Area of the...
Yes,
Okay.
area 2. Okay, look. Between 10 and t prime, okay, I have the velocity is decreasing. And because the area is under the graph, when the area is under the graph, I put delta V is negative.
Negative.
Okay, so now I can write for the second phase, I can write that the velocity at t prime minus the velocity at 10 seconds, okay, is equal to minus A2, because my graph is below the axis of time. Now, I know that the velocity at t prime is 0. So 0 minus, I already calculated the velocity at 10. Pay attention, please. The acceleration is discontinuous. So I have sudden decrease of acceleration from 10 to -2, but the velocity is continuous. So what will change then in the velocity graph is the slope. So in this part here, I can say the slope can be represented by phi. So phi was equal to 10, and suddenly at this point, the slope changed, and in this zone, I have a slope of -2. So what is discontinuous in the graph of v is the slope, but not the velocity. So the velocity will not change suddenly. It will have a gradual variation. So now it will be reduced from 100 to 0. I can say that here, if I replace in the formula, it's 0 minus 100 equals to -a2. Okay. Now, what is the expression of the area 2? If I look at my graph here, this is a rectangle. Okay. This rectangle is characterized by a certain height. This height is equal to the acceleration, which is 2. And the width of my rectangle here is equal to what? What is the value of this width? It's delta t.
T prime minus 10.
Exactly. It's t prime, the final time, minus 10, which is the time of beginning of phase 2. So now if I replace in my equation, I get that -100 is equal to -2 times t prime minus 10. So this equation will give you t prime. T prime will be equal to 60 seconds, because minus and minus will give you plus. I take 2 to the other side, it's 50 and plus 10. So I deduce that t prime in total is equal to 60 seconds. So I was able graphically to determine what is the total time t prime needed to stop my car. Okay, so now I can annotate on my graph that this is equal to 60 seconds. Okay, and I am done with the graph of velocity. Now I know everything about my graph. T prime is known, and the value of velocities at the beginning and end of each phases are known. Any question on how we did the drawing of velocity with respect to time?
Yes, دكتور بس
Yeah.
one small thing. لما
Yeah.
كنا ب A1 كنا بنشتغل ب A1 ب constant velocity
Yeah.
positive.
Yeah.
مش كان فينا نقول A equal صارت slope times T V equal A بدون ما نقعد نقول area وهيك.
بلا بس بتصير عم تعمل analytical method. Sometimes they will force you to use graphical method. So you should be familiar with both, okay?
Perfect. Thank you.
You can do, of course, in an analytical way and say that the equation in phase 1 is V equal to AT plus V0, and V0 is 0 and the slope is 10. So during this phase, V equal to 10t. Of course you can. But this will be an analytical method. And if they told you determine graphically your variables, you should use the graphical method then. Okay? If they don't force you to use a method, you are free to use what you want. So understand both ways, okay?
تمام. Thank you.
Any other
Professor?
question? Yes?
Yes, I have a question. In A2, can't we just use the formula of the slope?
If you
For
use the
V,
form,
and
what
we
do you mean? Look, what do you
delta
mean
V
just
over delta T?
what do you want to use? You want to say A equal delta V over delta T? You are using then
Yes,
an
and A
analytical
is
way.
-2.
Okay, but this is not a graphical method. This is analytical method. Yes, of course you can. Okay. This is the question of your friend. Look, you have two methods here. You can go to the analytical way and find the expressions of your velocity and the acceleration with respect to time. Okay, and then find t prime using analytical method by setting velocity at t prime equals to 0. But as I told you, sometimes they force you to use the graphical method, so you should be aware of both methods and know how to apply them. I will do for you the analytical method
Okay.
now. Okay, so if you want to use analytical method, not a graphical one, you say that in phase 1, I know that the acceleration is plus 10. And I know that by definition, the acceleration is derivative of velocity with respect to time. Okay, so then I can say that v is at plus v0. And since v0 is 0, then it will cancel out. And the value of a is just equal to the slope, which is 10. So during this phase, velocity is equal to 10t. And now once I have the equation, I can determine what is the velocity at 10 seconds. So I just replace. I say that v at 10 seconds, it's 10 times 10, it's equal to 100. So I obtain exactly the same result of the graphical method. Now, once I know the velocity at the end of phase 1, I say that this corresponds to the initial condition of phase 2. Because the velocity at the end of phase 1 is the velocity at the beginning of phase 2. And then in phase 2, I can say, so now in phase 2, I also can use that a is dv by dt, but now it's a negative slope, so it's minus 2. Okay, and then I do the integral procedure will be, I can do or separation of variables or simple integration. So I can say that velocity is equal to, here pay attention, okay? Velocity is minus 2t plus a constant. Now how to get this constant? Which condition I will use to get this constant? I need a boundary condition to get this constant. At what point I will use the boundary condition?
t equal 10 عشان
Exactly. At t equal 10.
last
Okay. Please pay attention, not at t equals 0, because point 0 is not a point of phase 1, of phase 2, it's a point of phase 1. So to get the constant, I should use this point. And I know for this point that at t equal 10, v is 100. So I just have to replace 100 equals to minus 2 times 10, which is 20, plus the constant. So I deduce that my constant is equal to 120. And now I have the expression of velocity in second phase. I can solve for t prime. How can I solve for t prime? What should I do then?
v equal to 0.
Exactly. I say that minus 2t prime plus 120 equal to 0. So I get t prime